Hi, welcome to our CS2100 Tutorial 7 discussion. So in this tutorial, we're going to be discussing Boolean algebra and logic gates. Okay, so I provided a summary of the rules, okay, and laws of Boolean algebra, and we will be looking at how we can apply these rules for the questions here. So in our first question, Boolean algebra, we are given this expression and with us to simplify them. Okay, so let's look at the first expression here. So 1a. So f x y z is equals to x plus y dot z bar dot y bar plus y plus x bar dot y dot z bar plus y. Okay, so let's look at what are the rules we can use. So if I look at this y bar plus y, this is actually my inverse or complement law over here. So a plus a bar equals to 1, a dot a bar equals to 0, all right? So any literal here plus the complement of it will always be equals to 1. Okay, so in this case, y plus y bar will always be equals to 1. So over on this left hand side, all I have is x plus y dot z bar. Now over on this right hand side, what do I have? I have plus x bar. This y dot z bar plus y. So you can see is y plus yz bar. And this is actually same as your absorption application of your absorption rule here. Okay, so you can see that this effectively, this whole term, okay, it becomes just y, okay, by the absorption rule. So it's x bar y. Okay, so I'm just going to now rearrange it. So the x, this x comes here, this x bar y, I'm going to write it first here, plus y dot z bar. Okay, now what do you see? This x plus x bar y becomes this absorption variant over here that you can see. So it becomes x plus y. So x plus y over here, okay, plus y dot z bar. Okay, and now this y plus yz bar also becomes a similar absorption rule as what you can see over here. So this whole thing also becomes y. So the final answer will now become x plus y. Okay, so that is your final simplified answer for 1a. Okay, so now let's look at 1b. Okay, so 1b. Okay, so 1b, we are given this expression. So this is a max term expression. Now, for a max term expression, basically what does that mean? That means, okay, these are the combinations 5, 9, and 13 that give us an output of 0. Okay, so if I were to draw the truth table, okay, so it will look like this. So I have P, Q, R, S. Okay, truth table. Okay, this is G. Okay, so of all the 16 possible combinations, the combination of 0, 1, 0, 1, 1, 0, 0, 1, and 1, 1, 0, 1 will give me 0, 0, 0. And everything else, okay, would give me a 1. Okay, everything else will give me a 1. Okay, so only these three combinations of 5, 9, and 13 give me a 0. So that is what we mean by a max term expression. So when you want to write it in terms of the literals, okay, what we need to remember is for a max term, we need to provide the complement of the literals when we're doing the expression. So what do I mean by that? Okay, so for example, 5, if I were to take number 5, a value 5, to normally represent it, I will say it is 0, 1, 0, 1, correct? And that would mean in terms of PQRS, it will be equivalent to P bar Q R bar S. Okay, but that is if I were to use a Minterm approach. Okay, but for a max term approach, I have to use it in the complement way. That means it will be now P plus Q bar plus R plus S bar. Okay, so that is how you represent uh, the maxterm expression. So 5, 9 and 13 would now be represented as P plus Q bar plus R plus S bar. Okay, so it is a product of some expression. So 9 is now P bar plus Q plus R plus S bar. Dot 13 will be P bar plus Q bar plus R plus S bar. Okay, so that is our initial step. Okay, so getting from the expression, maxterm expression, to all the representation in the literals. Now, what we can do is we can apply the rules that we know. So the first rule that we're going to apply is the distributive rule. So we can see that this Q bar R S bar and Q bar R S bar are common. Okay, so distributive rule says that I take out what is common. Okay, and the remaining is I do an OR operation with the product of the remaining terms. So the remaining terms are P and P bar. So P dot P bar. Okay, so there's a bigger bracket over here, dot with whatever is remaining, P bar plus Q plus R plus S bar. Okay, so this P dot P bar. Okay, so again this is a complement law, which means that P dot P bar will always be 0. Okay, and I do an OR operation with a 0 means nothing changes. So what is left is Q bar plus R plus S bar product with P bar plus Q plus R plus S bar. So again, I can look at the distributive law again, and I can say that R plus S bar and R plus S bar are common. So R plus S bar is here, plus, okay, the product of the remaining terms, which is Q bar dot with P bar plus Q. Okay, and this you can apply your absorption rule. Okay, so over here I can apply the absorption rule. Okay, and I'll get R plus S bar plus Q bar P bar. Okay, so again you can refer back to our absorption rules over here. Okay, so there are a few variants here, and apply the absorption rule to get the final answer here. Okay, so for 1B, that is your final simplified answer. Okay, so in general, Boolean algebra can be a bit tedious. Okay, and sometimes, you know, with so many rules and laws, it can be a bit daunting to know which is the correct rule to apply or which law to apply and so on. So that is where, of course, in the next tutorial, you're going to look at K-maps, which is going to make things a lot better. Okay, so of course with K-maps, your simplification is a lot better, a lot easier. Okay, so don't be too concerned. Okay, if you find that this is very, very tough or challenging, okay, K-maps is going to solve a lot of these issues very, very easily for you. Okay, in terms of simplifying a Boolean expression. Okay, so let's look at question 2 first. Question 2 is now telling us to express the functions in question 1 in the Minterm notation. Okay, so what do you mean by Minterm? Okay, so let's look at the expression first. So for A, what we have is function of x, y, and z is equals to, we know the final simplified version that we just had was x plus y. Okay, now when you say we want it as a Minterm expression, we are expecting to put some numbers here. Okay, so and since x, y, and z, you have 3 variables, so the numbers that I expect are from 0 to 7 over here. Okay, so that is what we know. And to get the number 0 to 7, I must know the values of all 3 variables here, x, y, and z. Okay, so now I only have x and y, and since x and y are both considered 1 and 1, okay, since it's a Minterm expression, I need to find the other combinations of y and z together with this x, and the other combinations of x and z together with this y. Okay, so how can I go about doing it? Okay, so I'm going to show you 2 approaches. The first one is the standard approach or systematic approach. Okay, so what you can do is, for example, you tackle it with one missing literal at a time. Okay, so for example, for x, you know that both y and z are missing here. So let's look at the y aspect first. So to include the y inside this expression, I do an AND operation with y plus y bar. If you look back at our laws, the identity law says that y plus y bar will always be 1. So x dot 1 will always be x. So logically, we're not changing anything. We're just adding the expression for y plus y bar, okay, into this expression here. Now we do the same thing for the missing, for the second term here, y, and we add in x plus x bar. Okay, so now what we can do is we can expand and we say xy plus xy bar plus xy plus x bar y. Now the next step is to repeat the same process for the next literal that you need to add in, which is z. So xy multiplied by z plus z bar plus xy bar multiplied by z plus z bar plus xy multiplied by z plus z bar plus x bar y multiplied by z plus z bar. Okay, so once all of that is done, then you can finally expand out everything. So you get xyz plus xy z bar plus xy bar z plus xy bar z bar plus xy z plus xy z bar plus x bar y z plus x bar y z bar. Okay, so with this you can now assign numbers to all of these combinations here, because all of these combinations have x, y, and z. Okay, so this will be 7, 6, 5, 4, 7, 6, 3, and 2. Okay, so the Minterm expression is 2, 3, 4, 5, 6, 7. Okay, so that is your final answer. Okay, so basically what we have done is for each of the literals, okay, we add in whatever is missing. So for x, y, and z is missing. For y, x, and z is missing. Okay, and to add in these missing literals, you multiply it or AND it with the literal or with the complement of itself. Okay, because this is always a 1. Okay, and you do it repeatedly for each missing literal at a time, and then you'll get a final expression where all the terms have all the literals inside. Okay, and then you can express it as a Minterm notation. Okay, so this is the systematic way of doing it. Now I'm going to show you a sort of a shortcut way of doing it. Okay, so how do we go about it? Okay, so what you need to do is, so what we need to do is, we know that we have x and y, and for x, what do we know? Y is missing and z is missing. And similarly for y, we know that x is missing and z is missing. So this big X here is basically to say that these are unknowns, correct? We do not know the combinations of these unknowns. So all we need to do is put in all the possible combinations of these unknowns. So its x means it's 2 unknowns, so the possible combinations are 0, 0, 0, 1, 1, 0, and 1, 1. Okay, same thing over here, 0, 0, 0, 1, 1, 0, and 1, 1. And since we know that x is also 1 and y is also 1, and then we have all the possible answers. So this is going to be 4, 5, 6, 7, and this is 2, 3, 6, 7. Okay, and if you take out the duplicates, you get the same answer as before. Okay, so this is a shortcut approach to getting or expressing your answer in a Minterm notation. Okay, so you can choose whatever approach that you think is most suitable to your understanding. Okay, so that is for part A. For part B, okay, so for part B, you are already given the max term expression, okay, which is given as 5, 9, and 13. Okay, and if you recall from your lecture slides, you would have realized that max term and min term are basically opposites. Okay, so max term, each of these numbers here is where the output is 0. For min term, the numbers are those where the output is a 1. Okay, so they're complement of each other. So the min term expression of this is basically all the other numbers: 2, 3, 4, 6, 7, 8, 10, 11, 12, 14, 15. Okay, so that is basically your final answer for part B. It's very easy since you already have been given the max term expression. You just look at all the other numbers which are not there, and that will be your min term expression. Okay, so that is your question 2. Okay, now let's look at question 3. In question 3, we are asked to fill up a truth table given the this POS expression. Okay, so we are given this expression that f a, b, and c is equals to a plus b bar dot a bar plus c. Okay, so how do we go about doing this? So this again comes back to the understanding of what is a POS or SOP. In SOP, each of the terms means it is the output is a 1. For POS, each of the terms is where the output is a 0. So this combination gives me a 0, and this combination also gives me a 0. Now let's look at this first combination, a plus b bar. So if you recall earlier, I said that in a max term expression, when you express it, the literals are inverted. So when you say b bar, it's actually when b is a 1 and a is a 0. Okay, a plus b bar means a is 0 and b is 1. Similarly, a bar plus c means a bar, that means a is a 1 and c is a 0 over here. Okay, now for this first expression, a plus b bar, c is not represented here. So what does that mean? That means c has in a way been simplified out of this. That means regardless of c, as long as a is 0 and b is 1, the output is going to be a 0. Okay, that's how you interpret this. So let me repeat that. So when you see that this expression does not have all the literals, that means some of these literals have already been simplified, okay, out. Okay, and what does that mean? That means in this first expression here, a plus b bar, a is 0, b is 1, and regardless of c, the output is going to be a 0. So if I look at the truth table here, a is 0 and b is 1 is this line and this line. So regardless of c, my output here is going to be a 0. Okay, the same thing applies over here. A bar or with c, that means when a is 1 and c is 0, regardless of b, my output is going to be a 0. Okay, so that is this line over here. A is 1, c is 0, and again a is 1, c is 0. So both of these cases, my output is going to be a 0 regardless of my b value. Okay, and the rest of the outputs here are going to be a 1. Okay, so that is basically how you are able to fill up a truth table given a POS expression. Now, what is the sort of relationship between SOP and POS? Okay, so what we can do is we can, given a truth table, okay, one way of getting the expression is, for example, if you are given the SOP of f prime, okay, so what is the SOP of f prime? So the sum of products is usually obtained by looking at the output where it's a 1. Okay, sum of product of f prime means I look at it when the output is a 0. Okay, when the output is a 0. Okay, now given that, okay, I can then do a invert to get the product of sum of f. Okay, so let's do this and see how we can go about doing and solving this. Okay, now given the SOP of f, okay, so let's look at the SOP of f. Okay, so sum of product of f, what do you have? So the sum of product of f is given as the minterm of 0, 1, 5 and 7. Correct? So if the sum of product of f is given as this, the sum of product of f prime is going to be sum of whatever is missing. Correct? So it will be 2, 3, 4 and 6. Correct? 2, 3, 4 and 6. So this is the sum of product of f prime. Okay, now what am I going to do next is I'm going to represent this in terms of its expressions over here. So SOP of f prime is now given as, so 2 is 0, 1, 0, which is a bar b c bar plus a bar b c plus a b bar c bar plus a b c bar. Okay, and I'm going to go ahead to simplify this first. Okay, so let's simplify this, and what can I see? I can see that a bar and b is a common term here, so c bar plus c plus again over here the common terms are a and c bar, so I have b plus b bar. Okay, so c plus c bar will be a 1, b plus b bar will be a 1, so left is a bar b plus a c bar. Okay, so this is the sum of products of f prime, okay, or f bar. Okay, and then to get the product of sum, okay, to get POS, I invert SOP of f bar. Okay, so let me write f bar. F bar is a bar b plus a c bar. So I'm going to do an invert operation. That means I put a bar here and put a bar here. So what will happen? So a bar b dot a c bar. So you're going to have a bar here and I'm going to have a bar here. Okay, and the final, so by De Morgan's theorem, I'll have a plus b bar dot a bar plus c. Okay, so let me explain this again. Okay, so if what we did in the first step is we are given a POS expression, and with this POS expression we are trying to fill up a truth table. So to fill up the truth table, we know that for a POS expression, each of the terms is where the output is a 0. Okay, so if the terms in this expression do not have all the literals over here, that means that one of those literals have already been simplified out. Okay, so for this expression, a plus b bar means a is 0, b is 1, and regardless of c, the output is going to be 0. And for this expression, a is 1, c is 0, so regardless of b, the output is going to be 0. Okay, so that is why we have the 4 zeros over here, and the rest are 1s. Now, in part B, they are so we sort of understand that the POS and SOP are complements, correct? The SOP is for output 1 and POS is output 0. So if I'm given SOP expression, how do I get the POS equivalent? So if I'm now given that the SOP of F is 0157, I can also use this information to come up with this truth table, correct? And because I'll know that these combinations of 0, 1, 5 and 7 are where the output is a 1 and the rest are all zeros, correct? And then what I can do is I can do a SOP of F prime or F bar. Okay, so the SOP of F bar means is the sum of product but where the outputs are 0. Okay, so the outputs are 0 for the combinations of 2, 3, 4 and 6. Okay, so I've written those down and I've simplified them. And finally, to convert this SOP to a POS, I invert the SOP of F bar. So this is the SOP of F bar. Okay, so this line here is the SOP of F bar. Okay, and if I invert the SOP of F bar, I'll get the POS of F. Okay, so this is F and this is the POS of F. Okay, so you can see that that is how you can relate SOP to POS. Okay, so even when you are doing the K-maps, you can apply a similar strategy. Okay, because when you circle all the ones, you get a Minterm expression for F. If you circle all the zeros, you get a Minterm expression for F bar. Okay, and then that will become, and when you invert that, that will become your POS. Okay, so you come to that. Okay, we will come to that when we start looking at the K-maps. Okay, so that is your question 3 to sort of understand the relationship between SOP and POS. Now, in question 4, and question 4 and question 5 are good questions to give you an idea of the kind of questions that are normally asked, okay, during assessments and so on, okay, where you are given some problem to sort of or challenge to solve, and you're supposed to first understand the logic behind it and come up with the truth table, and from the truth table you get a simplified expression, and from the expression you go on to design and build a circuit. Okay, so in this question you're having a voting machine where as long as you have two or more ones is considered a vote, correct? So in terms of logic here, this will be 0 0 0 1 0 1 1 1. Okay, and once you have this, we can have an expression for F, which is the Minterm expression, which says it is 3, 5, 6 and 7. Okay, so in terms of your logic, let's put everything down. So A B bar C plus A B C bar plus A B C. Okay, so to simplify this expression, again, once you learn K-maps, all this becomes very trivial, very easy. But just since this tutorial is focusing on Boolean algebra, how can you go about using the laws to solve it? Okay, so one of the laws says that you can sort of repeat the term again and again. Okay, so maybe I'll show you the law. So if you look at this item potency, I can keep on adding the same term again and again and nothing happens because of all operation with itself will effectively not change anything, correct? It's the same term again and again. So what I'm going to do here is the term here ABC, I'm going to keep on repeating it for the other terms. So this will be the one combination, plus A B bar C plus ABC, this is another combination, and this is the third combination. Okay, so I've repeated the term ABC 3 times, and the main reason is because I want to be able to factorize out, okay, the common terms and then do some simplification. So for the first pair here, PC is common, so I can factorize out A bar plus A, and similarly over here, AC is common, so I have B bar plus B, and finally over here I have AB is common, C bar plus C. Okay, so just now from the rules we also know that A plus A bar will always be equals to 1. So all I left is BC plus AC plus AB. Okay, so once you have this, basically it is quite a simple logic, so you can straight away implement it, okay, using your approach of logic gate. So you have A, B and C. So A and C is an AND gate over here, A and B is an AND gate over here, and okay, so this is AB, sorry, this is AC, this is AB, AC, AB and BC. Okay, so B and C. Okay, so I just do a OR operation here, and then you get it. Okay, of course they also ask you to implement it using only NAND gates. Okay, so in order for you to do that, what you need to do is you need to apply your De Morgan's theorem. So BC plus AC plus AB. Okay, so if I apply the De Morgan's theorem, what will I get? That means I put a double bar here. So I have BC dot AC dot AB, and the bar is still here. So the same thing. Okay, so A, B and C. Okay, but now is going through a NAND gate, AC, AB and BC. Okay, so in terms of circuit design, okay, why would we sometimes want to just stick with a single type of gate is because as you will see in the lab, each IC chip only has a fixed type of gate. So if you want an OR gate and you take an IC chip for the OR gate, inside that chip you only have OR gates. Okay, so if it's an AND gate IC chip, inside the chip only has AND gates and so on. Okay, so if I have a circuit design with a lot of different gates, then I may need a lot of IC chips. Okay, whereas if I can uh, have the design with only a particular type of gates, then I may be able to reduce the number of IC chips that I actually need in the physical implementation of the design. Okay, so that is where things like this come in handy. Okay, so for the last question, question 5, we are going to do a divide by 3 circuit. Okay, so this divide by 3 circuit, basically we are given a 4-bit number, unsigned binary number, and the output is a 3-bit unsigned binary number XYZ, where we're only looking at the quotient of ABCD divided by 3. Okay, so you can see that 0, 1 and 2, when I divide by 3, the quotient is 0. Similarly, when it is 3, 4 and 5, the quotient is 1. Okay, then 6, 7 and 8, okay, it is 2. Then 9, 10 and 11, it is 3. Okay, and then 12, 13 and 14, it is 4. And 15, it is 5. Okay, so this is the first step. Okay, and I must emphasize this again and again. Your truth table that you derive from the question is very, very important, because if your truth table is wrong, then all your following steps will be wrong. Okay, so I repeat again and I stress again, in any assessment, the exam and so on, when you're given a question like this where you're supposed to analyze the question and then from there derive a truth table and design a circuit and so on, after you come up with a truth table, please stop and check through one more time that you have understood the question carefully and you have implemented the truth table correctly. Okay, check it one more time just to make sure that everything is correct, and then you go on. Okay, so once the truth table is there, from there you are asked, okay, to implement, okay, or obtain the simplified expressions, okay, for x, y, and z. So we have a 3-bit output here, okay, x, y and z. So you need to come up with expressions for each of them. okay, for each of them. And for each of them, you also need to simplify and then come up with a circuit design. Okay, so there will be total of 3 Boolean expressions, okay, and which you need to then simplify and then implement as 3 separate circuits. Okay, so I'm not going to go into the details of this design. I'm sorry, in the details of the Boolean algebra simplification. Okay, so the answer is shown here. Okay, so what I want to say is, I understand that it is a bit daunting, okay, when you look at all the rules and laws, and sometimes you're not very sure how to proceed, correct? So that is where the K-map comes in to really help you to make this simplification a lot easier, okay? But what I want to show or emphasize is how sometimes analyzing some patterns in the truth table can help you a lot, okay, in the simplification process, okay? So for example, over here, if I were to look at x, okay, if I were to look at x alone, you can see that x is a 1, okay, only in the last 4 entries of the truth table. Okay, and in the last 4 entries of the truth table, you see that, okay, a and b are 1, and regardless of c and d. So c and d have all the 4 possible combinations, but regardless of any of the combinations, as long as a and b are 1, x is 1. Okay, so from this observation, you can see that c and d actually have no impact on x. X has a direct relationship only with a and b. Okay, so you can sort of intuitively say that x is a dot b. Okay, so if you just write out the values, okay, for a, b, c, d, you will see that 1 1 0 0, 1 1 0 1, 1 1 1 0, and 1 1 1 1. So regardless of any combination of c and d, as long as a and b are both 1, the output here of x will always be a 1. Okay, and something similar you can also do for y. Okay, so if you look at y, okay, so let's look at the cases where y is 1. Okay, so the combinations are 0 1 1 0, 0 1 1 1, 1 0 0 0, 1 0 0 1, 1 0 1 0, and 1 0 1 1. Okay, so if you look at these combinations, okay, so you can sort of break them up into 2 sections over here. Okay, so in this first section here, you can see that as long as a is 0, b is 1, c is 1, regardless of d, y is a 1, correct? So this translates to a bar, b, c. And if I look at this section here, again something similar. As long as a is 1 and b is 0, regardless of c and d, my output here is always going to be a 1. Okay, so you can see that this or this, okay, is what is given here. Okay, and x here is given here. Okay, so this is again a technique of sort of analyzing some patterns in the truth table, and then from there sort of deducing what the answer is going to be, even without sort of going through any Boolean algebra. Okay, but you don't necessarily have to do this approach, okay, because like I said, we have the K-maps which are there to help us with the simplification process. Okay, so with the K-maps, a lot of this will be much easier. Okay, so of course, only for x and y you can sort of see a pattern and do this. Z is not so obvious any pattern, so you still have to go through the whole process. Okay, and of course, after everything is done, then you can implement the circuit, okay, for x, y, and z. And if you implement the circuit, for example, x, we know that x is, okay, a and with b. Okay, will give me x. Okay, of course, if they also ask you to do the NAND gate approach, correct? If I were to do a NAND gate approach, so a being, if I were to follow De Morgan's theorem, so it will be a and b go through a NAND gate, and then I have to go to another inverter again, correct? So the other inverter could be a split input NAND gate. Okay, so that will be your X. Okay, similarly for Y, so again, what is your Y expression? A bar B C plus A dot B bar. Okay, so uh, in terms of direct implementation, we have A, B, C. So A bar, okay, with B and C, you have N here, and A dot with B bar here. Okay, sorry. Let me just check it again. A, B bar, correct. Yeah. Okay, so that will be your final. Sorry, and I need to go through an OR gate here. Okay, so that will be your Y here. So this is your A bar, B, C, and this is your A and B bar. Okay, A and B bar. Okay, so now, of course, if they ask you for the approach with the NAND gates alone, so it comes back to the same thing. So A bar, B, C plus A, B bar. So I put a double bar here. So what will happen? It will become A bar, B, C dot A dot B bar and this. Okay, so if I were to implement it, A, B and C. So A, again I have a split input NAND gate for the inverter. B and C, so that will be one NAND gate, correct? Then A with B bar over here. Okay, and then this two, another NAND gate. Okay, so this is how your final design will look like. Okay, so in this tutorial, we have sort of covered basics of Boolean algebra and implementation of a truth table, as well as implementation using logic gates. Okay, in the next few lectures, things are going to get even more exciting in the sense that we're going to have a lot more introduction to hardware in terms of adders, comparators, multiplexers, decoders, encoders, and so on. Okay, so things are going to get a lot more exciting, uh, and everything builds up. Okay, everything builds up. So if you get lost in one of the sections, you may find that subsequent lectures may get even more confusing. Okay, so if you have trouble understanding any of this stuff that we have that we are going through in the lectures or tutorials, please seek help early. Okay, don't wait until the reading week. Okay, you are free to approach me or approach your tutor or your lecturer, okay, to clarify and clear all your doubts early. Okay, so please don't wait till the end. Okay, and you know you just get even and more panicky. Okay, so try to seek help early and clear any doubts that you may have. Okay, so thank you for watching the video, and I hope that this helps you with your understanding of your tutorial 7. Thank you.